Hello, AP Chemistry. How are we doing? Hopefully, y'all are doing well. So, today we are going to be continuing our Unit 8 notes on acids and bases. And the lesson today is going to focus on bases and salts. Now, we're going to start with bases. The very first thing is we need to be able to recognize what is a strong base. Now, the most common thing that we talk about for strong bases are our hydroxides, specifically the group 1 and group 2 metal hydroxides. So group 1, we know it's everything in group 1 with the exception of the first one, so hydrogen. Why? Because hydrogen hydroxide is water. It is H2O. For group 2, we know it is everything in group 2 with the exception of the first two. So the exceptions for that would be beryllium and magnesium. And those are our exceptions. Okay, so we do need to keep that in mind. We need to be able to recognize what we have as a strong base when we look at a problem. Okay, now this first problem here says to calculate the OH concentration, the H concentration, and the pH of a 0.0100 molar solution of NaOH. Now, the very first thing is I'm going to go ahead and solve for my hydroxide concentration. I do that because I know that this is a strong base. I know that it will completely dissociate. And so whatever my concentration here is actually the concentration of my hydroxide. So my hydroxide concentration equals 0.0100 molar. Okay? Well, now I need to solve for my both hydrogen concentration and my pH. So luckily, I know that once I have my hydrogen concentration, I can solve for pH using my negative log. But let's go ahead and solve for our hydrogen concentration. One thing to remember is that our hydrogen concentration times our hydroxide concentration equals 1 times 10 to the negative 14. So if I'm solving for my hydrogen concentration, I would divide both sides by that hydroxide concentration. So I would have my hydrogen concentration equals 1 times 10 to the negative 14 divided by 0.0100 molar. Okay? So I plug that into my calculator and I find that my hydrogen concentration equals 1.00 times 10 to the negative 12. Let me erase that. Okay, so there would be my hydrogen concentration. Well, now I need to solve for my pH. So we know that pH equals the negative log of my hydrogen concentration. So to do that, pH equals the negative log of 1.00 times 10 to the negative 12. So I find my pH equals 12. And so there would be my 3 answers. Okay, so you do need to make sure that you know how to convert from these different things. Now, another thing that you could do is actually convert from a pH or a pOH to our concentrations using that 10 to the power of the negative whatever our pH or pOH is. Okay. All right. So we know about strong bases. Okay, we've been working with them for a while. Y'all worked with them in previous chemistry courses as well, but we never did work with a weak base. So let's actually talk about a weak base. Now, weak bases are going to be those bases without that hydroxide. They're going to react with water to produce a hydroxide ion. Okay, and so common examples of weak bases are going to be things like ammonia or methylamine or ethylamine. And so when I'm looking at those, we do need to be able to recognize that these are going to be a weak base. So how do I do that? Well, our kind of basic formula for this is I'll take some kind of base, I add it into water, and it results in a conjugate acid and a conjugate base. Well, we know that, right? Well, a big important concept is that we are producing that hydroxide ion there. So one of these hydrogens on the acid actually pairs up with that base there, okay? So, for example, here I've got my NH3. We know NH3 is a base just based off of what I just told you, right? So NH3 plus our water NH3 is acting as the base, water is acting as the acid. So we know that the acid donates a proton, the base accepts a proton. So we see this NH3 turn into NH4. And so it accepted that proton. Well, now I've got NH4 here, which is the conjugate acid of that. And I've got my conjugate base there, which is OH minus, because it has lost that hydrogen ion. Okay? So keep in mind that you are going to have to be able to recognize what these weak bases are and what are the results of that. So be able to write a formula that involves this transfer of those protons. Okay? So when we're looking at this, one thing to keep in mind is that the lone pair on that nitrogen is basically going to form a bond with the hydrogen ion. And we know that most weak bases actually involve that nitrogen because that is how that bond is actually going to form. Okay. Now, moving on. If you remember last class when we were talking about solving for a weak acid, we talked about the acid dissociation constant, that Ka. And so with weak bases, we're basically going to do the same thing. We've got the base dissociation constant, which is Kb for the base, right? And so I know my Kb is going to be my basic acid there, that conjugate acid there, and then my hydroxide, and then it's going to be divided by that base concentration. So really we're going to be doing the same thing that we did with our weak acids in terms of determining what that hydroxide concentration will be. All right. Now, when we're determining the pH of a weak base, it is very similar to the determination of pH of a weak acid. Again, we're going to follow the same steps. However, I want to remind y'all that when we solve for this base dissociation constant, we're going to be solving for the hydroxide concentration, not the hydrogen concentration. So that's the big difference between the weak acid and the weak base. When we did our weak acid, we solved for that hydrogen concentration, that hydronium concentration. But when we solve for our base dissociation constant, we're solving for a hydroxide concentration. Okay? So do keep that in mind. We are working with OH, not H. Okay? So here it says calculate the OH minus, the hydroxide concentration and the pH for a 15 molar NH3 solution. And they tell us that the base dissociation constant is 1.8 times 10 to the negative 5. Okay, so the very first thing that I need to do is actually write out my Rice table. So my Rice table, my reaction is I took some ammonia and water, and it is going to react and form NH4 and OH minus. All right. I know my initial concentration is 15 for my ammonia. We do not worry about the water in any of these situations. Why? Because water is a liquid, and we discount our solids and our liquids. I know that I'm starting this, so we're starting with 0 of the NH4 and the OH. Our change is minus X for our reactants, and it is plus X for our products there. So our final here is going to be 15.0 minus X, and then X and X. Okay. Now, what do? Well, the next thing I would do is I would set up my equilibrium expression here. So I know my Kb equals the concentration of NH4 times the concentration of OH minus divided by the concentration of NH3. Okay, well now I would go ahead and plug in my numbers. Well, they tell us that the Kb for ammonia is 1.8 times 10 to the negative 5. That equals X squared over 15.0 minus X. Now we do need to recognize that our K value here is negligible. And so what we're going to do is we can actually get rid of this X right there. And then it's just a matter of solving for our X value here. So I find that X equals, I'm going to rearrange it a little bit. x equals the square root of 1.8 times 10 to the negative 5, and I took that and I multiplied it by 15. So I found that my x equals 0.0164 molar. Okay, so that would be my concentration there. That is specifically the hydroxide concentration. So the concentration of hydroxide. Okay, so I solved for the first part of my question, but it also asked me to solve for my pH. So here is my first answer. But I'm not done because, again, I need to find my pH. So now what I need to do is I need to take my hydroxide concentration and convert it into that pH. My suggestion is you go ahead and take the negative log of this. That's going to give us our POH. So I would find my POH equals the negative log of my concentration here. So 0.0164. And I find my POH equals 1.785. Right? So now I've got my POH, but again, my question asked for pH. So I know that pH equals 14 minus my POH, 1.785. And so I find my pH to equal 12.215. And then that would be my answer there. All right. So now we've got our weak bases down. Again, basically the same thing as what we were working with our weak acids. But again, we are going to be solving for hydroxide, not hydrogen. So now let's look at our neutral salts. So neutral salts are going to be formed when we take the cation of a strong base and the anion of a strong acid, and they're going to form that neutral solution when dissolved in water. So an example of this would be NaCl, table salt, right? So Na is the cation of a strong base, sodium hydroxide, okay? Cl is the anion of a strong acid, HCl, hydrochloric acid there. So if I've got the cation of a strong base and the anion of a strong acid, that is going to be a neutral salt. Okay? If I've got an acidic salt, what we're going to have is the cation of a weak base with the anion of a strong acid. All right? So the cation of a weak base with the anion of a strong acid. And they're going to form when that acidic solution will actually dissolve in the water. So, for example, I've got NH4Cl. Basically, what's happening is that cation hydrolyzes the water molecules to produce hydronium ions. So we've got that H+, right? That H3O+. And thus, it's going to form an acidic solution because we've got those hydrogen ions floating around. Basically, that anion is going to become a spectator ion. It's not actually doing anything in that reaction. Okay, so here I've got NH4 plus H2O, and a reversible reaction is going to produce H3O plus and NH3. So we know that NH3 is a weak base. That is a very common weak base that we work with. So I've got my weak base, and I've got my strong acid, which is, again, basically this hydrogen ion that we are working with. Basic salts. So with basic salts, it is the opposite of with acidic salts. So you take the cation of a strong base and the anion of a weak acid, and then they are going to form or dissolve in water. And as a result of this, we're going to produce hydroxide ions, and then the cation is my spectator ion. So basically what we're trying to keep in mind, what we're trying to focus on is I need to be able to identify if something is a strong base or a strong acid, a weak base, or a weak acid. Because that is what we're going to have to look at and see, okay, well, if I've got a strong base and a weak acid, their cations come together to form a salt. That salt is going to form basic salts. Next thing, when we're determining the pH of a salt solution, one of the things that we can use are those dissociation constants for either the acid or the base, that weak acid or that weak base. And we will use that because we know that if I take the dissociation constant for our acid, the dissociation constant for our base, and I multiply those two numbers together, we know that that equals the dissociation constant for our water, which is 1.0 times 10 to the negative 14. All right. And so I can take my dissociation constants for my acid and base, multiply those two numbers together, and I will equal 1 times 10 to the negative 14. So if I've got either the acid or the base, I can solve for the other. All right. So now let's take a look at this example here. So it says calculate the pH of a 0.15 molar solution of sodium acetate. The Ka of acetic acid is 1.8 times 10 to the negative 5. Okay, so what do I do here? Well, the very first thing that I need to do is I need to recognize what is going to happen in this case. Well, in this case, what we're going to see is that that acetate is going to react with that H2O, and it's going to kick out a hydroxide. For my reaction here, I've got my sodium acetate. Now, in this case, I know that sodium is going to be a spectator ion. Why? Because it's going to produce sodium hydroxide. Well, sodium hydroxide is a strong base. We know that that will completely dissociate, right? And so we know that sodium is going to be a spectator ion. It's not going to do anything in that reaction. So in this reaction, really what I've got is my acetate and water, and it's going to produce this acetic acid and a hydroxide ion. Okay? So that is my chemical reaction. All right, so there is my reaction. Well, now I can go ahead and write my Rice table. So my initial amount was 0.15 molar. Again, I don't worry about my water at all because it's a liquid. I start with 0 of the acetic acid and 0 of that hydroxide. My change is minus x, and plus x. So then my final would be 0.15 minus x, and x. So now, looking at this, I know that when I solve this equilibrium expression, I've got my Kb. I know that it's Kb because I've got my hydroxide ion that is being produced, okay? And so I need to keep that in mind when I'm solving this problem. Well, here's the thing. They did not give me Kb when I was solving this problem. They gave me Ka instead. So what do I need to do? Well, one thing that I know is that Ka times Kb equals my Kw. And I do know that my Ka is 1.8 times 10 to the negative 5, and it times Kb equals 1.0 times 10 to the negative 14. So now I'm going to rearrange my equation and solve for my Kb. So my Kb equals 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And I find that my Kb equals 5.6 times 10 to the negative 10. All right, so I've got my Kb. Let's go ahead and write our equilibrium expression. So I know that Kb equals the concentration of HC2H3O2 times the concentration of hydroxide divided by my concentration of my acetate here, C2H3O2 minus. So then I found that my Kb was 5.6 times 10 to the negative 10, and that equals x squared over 0.15 minus x. I rearrange this and I solve for my x, and I do make the assumption that this x here is negligible. So then I find that my x equals 9.2 times 10 to the negative 6 molar, and then this is going to be for my hydroxide ion. Okay. Now, here's the thing though. They asked me for pH. So how do we do? Well, my suggestion is you solve for my pOH. So it is the negative log of my hydroxide concentration, 9.2 times 10 to the negative 6. So then I find my pOH to equal 5.04. And then I know that pH equals 14 minus 5.04. So then I know my pH equals 8.96. And then that would be my answer. So the important thing about this is that when you're looking at these, you're recognizing what's going to happen in this reaction. When that salt reacts with that water, what is going to be the result? Okay? Now, sometimes you might be asked to determine the general order of pH. This is the order of pH in terms of from high to low. So as I move from high to low, this is decreasing pH. We know that bases, strong bases specifically, have the highest pH. And as we move down, so weak bases, then basic salts, then we've got our neutral salts. So neutral salts will be around 7, right? And we keep going down until eventually we end up with our strong acids, which have that lowest pH that we've got there. Okay? So right here, it asks us to arrange the following 0.1 molar solutions in order of decreasing pH. So in this case, I've got to know, are these weak acids, weak bases, strong bases, basic salts, acidic salts, or neutral salts? I've got to be able to identify them as all of these things. And so when I'm going through to identify these, I need to recognize what they are. Okay, first off, I've got sodium hydroxide. Well, sodium hydroxide is a strong base, right? We know that it is something with group 1. It's paired up with a hydroxide, so it is a strong base. What about this NaCN? Well, I've got this sodium cyanide, and I know that this doesn't fall into the category of an acid or a base. It falls into the category of a salt. So I need to know, is this a basic salt or is this an acidic salt? And so what I need to do is I need to look at the ions that we've got. This right here is this is a cation of a strong base, right? This is going to be something from group 1. If it were paired up with hydroxide, just like we see right here, then it would be a strong base. So this is an ion of a strong base. Cyanide is the ion of a weak acid. HCN, cyanic acid, that is a weak acid there. So we know that I've got a strong base as our cation and a weak acid as our anion. So that would tell me that this is a basic salt. Okay, so now that y'all have kind of got a general idea of what to do, I want y'all to go ahead and try to label the rest of these as one of those 7 things. So strong base, basic salt, weak acid, weak base, strong acid, acidic salt, and a neutral salt. Sorry, I had a little trouble remembering all those. So I want y'all to go through and label these. So pause your video and then we'll go over it. Okay, so here is what you should have ended up with. So with my KCl, I know that K is going to be a cation of a strong base. Cl is an anion of a strong acid. So I've got strong base, strong acid. That makes this a neutral salt. Here, I've got methylamine. And methylamine is one of our weak bases, so that is something to take a look at there. Next, I've got H3PO4, so that would be phosphoric acid here, and phosphoric is a weak acid. Remember, sono, clo, clo, brickle, those would be our strong acids, so this does not fall into that. And then last, I've got an acidic salt. Now, again, I know this is an acidic salt, because if I've got ammonium hydroxide, that would be a weak base. I've got my HNO3, that would be a strong acid, right? And so strong acid, weak base, that would make this an acidic salt, all right? So then we would rearrange these, and then here would be your order in decreasing pH. So my sodium hydroxide would have the highest pH, and my phosphoric acid there would have the lowest pH. All right. All right, 2 final things to go over real quick, and this is just kind of to help y'all with some of this stuff. So if I've got acidic and basic oxides, this is something that's going to help you just be able to recognize quickly what we're working with. So if I've got a metallic oxides, when I put them in water, are going to dissolve or produce a metallic hydroxide. So if I've got a metal oxide bonding or mixing with water, it's going to produce a metallic hydroxide. We know hydroxides are basic solutions, right? So if I've got a metallic oxide, it makes a basic solution. If I've got a non-metallic oxide and it's dissolving in water, it's going to produce a weak acid. So it's going to make an acidic solution. So metallic oxides in water make a basic solution. Non-metallic oxides in water make an acidic solution. Okay? And then if I've got a salt and I'm trying to figure out what's going on with it, if it's got a very large charge, for instance, aluminum bonded with chlorine, aluminum's got a +3 charge, then it's going to form an acidic solution. If I've got iron with a +6 charge, it's going to produce an acidic solution. Lead with a +2 charge, again, well, +4 charge, it is going to produce an acidic solution. So when you've got a very large charge, you produce an acidic solution when we're working with that metal ion, okay? So the higher the charge on the metal, all that to say, the higher the charge on the metal, the stronger the acidity of that hydrated ion. And that's basically because those electrons are pulled further away from that hydroxide or that oxygen to hydrogen bond, and they're going to be being pulled towards our metal ion. So if we've got that greater positive charge, we're going to see an acidic solution start to form there. All right, y'all, that is it for our bases and salts. As always, let us know if you've got any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.